A very good morning to all participants. My dear colleagues. Good evening, Professor Prasant Mohapatra, Distinguished Speaker, Fellow IEEE, Vice Chancellor for Research, Distinguished Professor of Computer Science, University of California, Davis, US. I welcome you all to NIT Rourkela. We are very much thankful to Professor Mohapatra, sir, as you have given your valuable time to deliver a talk on millimeter wave sensing, millimeter wave for smart sensing. I am very happy to share amongst the participants that Professor Prasant Mohapatra is an alumnus of NIT Rourkela. Now, let me read out a brief biography of Prasant Mohapatra. Professor Prasant Mohapatra is serving as the Vice Chancellor for Research at University of California, Davis. He is also a distinguished professor in the Department of Computer Science and served as the Dean and Vice-Provost of Graduate Studies at University of California, Davis during 2016 to 18. He served as an Associate Chancellor during 2014 to 16 and the Interim Vice-Provost and CIO of UC Davis during 2013 to 14. He was the Department Chair of Computer Science during 2007 to 2013 and held the Team Bucher Family Endowed Chair Professorship during that period. In the past, Professor Mohapatra has been on the faculty at Iowa State University and Michigan State University. He has also held visiting scientist positions at Intel Corporation, Panasonic Technologies, Institute of Infocomm Research, Singapore, and National ICT Australia. He has been a visiting professor at the University of Padova, Italy, Yonsei University, and KAST, South Korea. Professor Mohapatra was the editor-in-chief of the IEEE Transaction on mobile computing. Professor Mohapatra has served on the editorial board of the IEEE Transactions on computers, IEEE Transactions in mobile computing, IEEE Transactions on parallel and distributed systems, ACM, WINET, and Ad Hoc Networks. He has served as the program chair and general chair and has been on the program organizational committees of several international conferences. Professor Mohapatra has been a guest editor for IEEE Networks, IEEE Transactions on mobile computing, IEEE Communications, IEEE Wireless Communications, and the IEEE Computer. Professor Mohapatra received his doctoral degree from Penn State University in 1993 and he received an Outstanding Engineering Alumni Award in 2008. He is also the recipient of the Distinguished Alumnus Award from National Institute of Technology, Rourkela, India. Professor Mohapatra's research interests are in the areas of wireless networks, mobile communications, cybersecurity, and internet protocols. So, thank you, sir. Thank you for joining us today and giving us your valuable time to deliver this talk on millimeter wave for smart sensing, which is a very research, it has research potential, high research potential for this 5G and upcoming 6G research. Thank you, sir. Over to Professor Mohapatra.
Thank you, Professor Das. That was too long an introduction. Let me see if I can share my screen.
Yes, sir.
Okay. can you all see my screen now?
Yeah, perfect. Perfect,
Okay.
sir.
So first of all, thanks a lot for inviting me. It's always a pleasure, and I have a lot of excitement to speak to my alumni organization, my home institution back in India. So 33 years and still counting. I graduated in 1987, and the campus looked much different than what it is looking now. The world also looks much different. So, but it's always a pleasure to talk to faculty of NIT Rourkela, and I do have quite a bit of points of contacts with the institute, and I do take a lot of pride in that. So I was looking at the agenda for this um, short course, and the focus is on 5G, and I wanted to see what are the different talks in there. And when I first looked at it, and I had the advantage because I was probably the last one to give the title. So I was wondering what should I talk about. I've done quite a bit of work on different aspects of 5G, but I noticed that almost all the talks are focused on the communication aspects of millimeter wave. So that's why I chose a different topic on how we can use millimeter wave, which is the foundational technology behind 5G, how we can use that for very smart sensing. So that will be the theme of my talk over here, that we can leverage, in addition to high bandwidth, in addition to the reliability, in addition to the speed of connections and all, we can also explore the use of millimeter wave for various types of sensing. So that essentially is the theme. So again, I'll keep the context and the content very simple. There are two applications that I will talk about, and I'll show the experiments that we have run. So nothing in tonight's, okay, it's night here, nothing in this morning talk will be related to any kind of analysis, modeling, or simulation. I'll show you real experiments that we have done using millimeter wave, and you'll get a flavor of how we can use millimeter wave for other applications rather than just for communications in 5G, 6G, and beyond. So there are two broad applications I will look at, and I'll pick one example of that. One is related to human health. The other is related to food and agriculture. So there are only two parts of this talk, and before the end of the talk, I'll also give some pointers for future leads related to research on these topics. So first, let's talk about human health issues. So what my vision here is that can we create an environment where your vitals can be monitored seamlessly without any imposition on you or any kind of. So for example, let me take an example. If I'm not feeling well, you will have to, the doctor checks the heartbeat, the breathing rate, and whatever, any other vitals that the doctor need. We'll take the simple examples of vitals today. We are looking at other complex vital situations in our ongoing research, but let's focus about the breathing rate and the heart rate just for today. Now, is there a way that someone could be monitoring my breathing rate and heart rate without even me, knowing about it? Knowing means I would have given my consent. So I'm not talking about privacy issues or anything, but I've given my consent. But if I walk into, let's say, a facility, if I want to walk into a doctor's office, instead of somebody measuring it, can I just walk through and on the screen, my breathing rate and heart rate can appear? Similarly, just think about it, pushing it further. Can I have a system implemented at my home that the devices are continually monitoring my breathing rate and heart rate without me doing anything about it? So they sense it from the air, like any other wireless sensors, and they monitor that. And in case there is a problem, something gets triggered, and there are actuators and all those things. So we'll not get into that part in there. There are different challenges in there because note that in any environment, so I'll take the example of an office space or a home environment. There are multiple people in there. So, okay, you don't want to confuse one person's heart rate with another person's heart rate. So that's kind of the goal that we are looking at, that can we create an environment where we can sense seamlessly and also safeguard against confusion when there are multiple people in there. So what we look at, so I'll show you some of the experiments that we have done, and that will give you a flavor of the potential this has. Again, these are all new technology. None of this, I'm upfront admitting, none of these is full scale vetted out, but this will expose you to the opportunities and possibilities that you may have in pursuing research in this direction. So we took 60 gigahertz millimeter wave. 60 gigahertz is an unlicensed band. I think it's from 57 to 64 gigahertz. There is a 7 gigahertz band over there, which is unlicensed, like the 2.4 or 5 gigahertz band. So it's freely available. So we wanted to use that. And the idea over here is that, of course, you can use the same band, the 60 gigahertz band, for communication purposes, which gives you a bandwidth of almost 6 to 7 gigabits per second, as we have measured, but in the indoor environment. But again, as I said, I'm not going to talk about the communication part, but I'll focus primarily on the sensing part. But you can use this environment as sensing, in addition to running your, let's say, your high definition video streaming and all that in indoor environment. So what we are trying to do is, we will have these millimeter wave signals reflected off human body. And what we have seen, that even the minutest chest movement that we all have while breathing, and the heart rate, that can be captured and measured through the sensing environment. And I'll show you the experiments that we have run. So, but due to the, as you know, that due to the, this high frequencies have high attenuation rate also. So we use directional beamforming signals in order to reduce the losses due to attenuation. And the other thing is, think about it, the logistics for arranging it. There'll be, if we are trying to monitor the vitals of human beings are not stationary at one place, they may be moving. So how do you capture all that? And but there is another advantage to the directional nature of those, or the beam forming of the signal, is you can have spatial reuse, where you can capture multiple human beings. So let me tell you the experiments that we have run. And again, we have this setup, and as you can see, this is very crude lab type of setup, but you can make it very fancy. So I don't know whether you see my cursor in here or not, but we have on the right hand side, we have the transmitter. So this is the 60 gigahertz transmitter. This is the 60 gigahertz receiver over here. And we use horn antennas. So these gives beams. So it has about 3 decibel beam width of 12 degree. And these are on, again, many of these things we created. Oops, sorry. Where did it go? Okay. So these are on this the base, which can rotate pretty freely. So these are in the base, which, because we can do all the angular adjustment on this. And on the transmitter side, we have a signal generator, and the receiver side, we are having the signal analyzer. And again, there are, so what basically we are doing is, we are looking at the received signal strength at the receiver side, and we are using that, the spectral density distribution that we get at the receiver side, we use that in order to extract the samples of the chest movement, or the the movement due to the heartbeats. So we capture about 62 samples per second. 62 samples per second are pretty good in terms of capturing the breathing rate and the heartbeat rate. And I'll show you the real results in the process also. So we call this system as millimeter vital. The name should be obvious why it is called that way. So the goal is, we use reflection-based monitoring which is robust to different incident angles. And as I said, we are using this horn antenna with this rotating platform, so it can adjust to any direction. So it can also point into the human bodies in different postures. And we have examined different posture, upstanding, sitting, sleeping, walking, and all. So before we start the vital signs monitoring, you need to first find out where is the human. Let's take one room, okay? There might be 2-3 people in there. You need to first find out where the person is. Again, there is no one standing there and pointing out the antenna. So we need to automate the whole process. So I'll talk about, monitoring the people in parallel and all that. But let me show you the overall schematic of how these things work. So we have the transmitter and receiver, as you see on the left top corner. So we have two modules in here. One is human finding subsystem. The other is the vital sign monitoring subsystem. So first, what is done is you create an omnidirectional sweeping process of the horn antenna. As I said, it can move almost 360 degrees, and you try to evaluate the reflection losses everywhere. And I'll get to that point. That's where we use some machine learning scheme also in order to analyze those reflection losses and then determine where exactly is the human. So basically, we use a machine learning approach in order to do a classification, and we will find out where the humans are. And I'll get into more details of that. Once that is done, then you basically beam the antennas towards the humans, and basically then you capture the RSS samples. As I said, we capture 62 samples per second, and then basically we do all the denoising and filtering in order to estimate the breathing rate and heart rate. There are a bit of mathematics involved in the denoising and filtering part, which I won't I'll skip that part. So what happens is when you capture, this is how the raw data, the blue graph that you see, the blue curve, that is the raw data. So we use FFT on the RSS time series data that you see in the raw environment. From there, we capture the the amplitude for capturing the breathing pattern as well as the heartbeat pattern. So what we do is we select the highest magnitude peak of adjacent beams because the movement of breathings are much higher than the heartbeat. So we capture only the adjacent beams, and from there we can capture the breathing pattern. For the heartbeat, we capture about 4 adjacent bins in order to capture the heartbeat in there. Again, there are more details to it, but if you are interested in more details, this is a published paper which is on my website. So once we use all the filtering and denoising pattern from the raw data, we can extract the heartbeat and the breathing pattern. So in order to measure the vital signs, again, we need to the angle between. So keep in mind that there's a transmitter and there's a receiver, and we are capturing the reflection of the 60 gigahertz beams from the human body. Okay, so this angle that you see, that also has an impact. So we call this as the incident angle. This angle has an impact. Just think about it. If there are 180 degrees, if this angle is 180 degrees, you may not be able to get much out of it. And so we did some analysis on how we can maintain a reasonable angle in order to extract better RSS value. And again, I'll skip this slide, but this is where we have all the details of how you identify what is an appropriate or a good incident angle. Okay. Now, so the other aspect is I should have had it other way. I told you that if we have identified the location of a human, then we can find out through the RSS measurements, we can find out or extrapolate the breathing rate and the heart rate. Now the question is, how do you find the human? So there are several objects in a room, in a lab, in a building. So there are many such things. So when you have objects, so let's say here is the transmitter again and the receiver. The distances of the object will be varying. So this is the distance between the two antennas, the transmitter and receiver. There will be many objects. From each objects, there will be some reflection losses and there will be path losses. So again, we have done all the analysis of that. What we have done is, if you analyze all of these, so here I'm giving you an example that my student did in one of our labs. So basically, if you look at the RSS loss in dB and the graph, so for each and every object in that room and human, we captured the RSS loss. So you can see that the computer monitors had certain loss. There was I don't know why they had a pressure cooker there, but it is what it is. Then the trash can, there's a difference between metal trash can and plastic trash can. And also you can see that the losses vary for different objects. And the last one is the losses at the human level. Again, if you have, and some of the things are obvious over here. If something is metal, then the losses will be very low because there will be good reflection from those objects with millimeter wave beams. So what we did is we have a very simple machine learning algorithm which does a broad classification from which we can capture. Given a room, through some quick learning process, we will be able to identify if there are if human beings are there or not, and if they are there, where they are. Okay, so that is primarily detecting the we create a heat map. So these are the actual measurements. I won't go through the algorithm over here. So this is in one of our labs. Okay, these are different objects. I know which object is where. These are different objects. And again, and this is where we have added human beings. So this is, for example, this is the reflection from a laptop. There is somebody in here, so we have this reflection in here. So with a simple learning algorithm, we use a learned classifier in order to identify human being. Once the human beings are there, then as I discussed about it, we can measure the heartbeat and the breathing rate. Now, so once we figured that out, then the question was, okay, what if we have multiple human beings in the room? How do we do that? So the same question happens that if there are multiple things in, then all rooms have multiple things. So what we realized that we can use multiple beams because of the beaming property of the high frequencies, we can exploit the spatial reuse in order to identify multi-beam sensing. We keep on changing the angle and try to sense multiple areas. So that way we can detect multiple human beings. So we can change the angular separation. So for example, let's say there are two human beings over here, A and B. Then we try to realize that, okay, you have so the idea, again, there are more details to it, but let me tell you this. So the idea is there are some static objects around it, and there are two human beings in here. So we try to find out by using two different angles. We again, shift the angular. We move the horn antennas over here to use two different incident angles. And there are, let's say, all these are different objects in there. Corresponding to each of those angles, all those measurements change. Now, when we have two human beings, for each of those, the classifier will identify the class which belongs to the human. So we were able to successfully determine multiple human beings using the same pair of antenna. Now, when we were doing this, we didn't have access to an array antenna. Again, most of these things at 60 gigahertz range, the equipments are expensive. So we wanted to reuse as much as we can. So if you have an array antenna, or if you have broad sense of series of angular antennas, you don't have to do this part. You can use them in parallel in order to get that. But even we wanted to, so let's say you want to market this application in civilian world, you have to make it cheap also. Why use so many antennas if you don't need those? So that was our main goal, to have an approach to monitor multiple human beings using the same pair of antenna. So again, I'll skip a few of the details over here. So the other thing that we wanted to also determine is when people are moving in a room or people have this different posture. When you are standing versus sitting on a chair or lying down on a bed and all. So we did a lot of analysis. I don't no, I don't have those slides in there, but we did a lot of those other type of variation study, and the results were pretty good in a way. So if you look at the here, I'm showing the results for different subjects. So we use the mean estimation error in order to measure the different with different angular separation. As you can see, as I mentioned over here, as you go to the higher angle, so if you let's look at the left graph, if you can see that the green ones, they have the green ones, the mean estimate error are higher. And again, these are for different subjects. However, it may not be always consistent. For example, in subject 4, the red one performs better than that. So there is no standard definition. You can say that one is better than the other. So, but since we are using a learning environment, we can quickly learn based on the size of the room, based on the objects in the room and all, and we could determine that the breathing rate and heart rate that we are capturing were very close to what you can measure in standard medical devices. So the few other things I want to show over here is when you increase the distance, high frequencies, the RSS loss increases with distance. So we have to, so here I'm trying to show the robustness with respect to distance and posture. So up to certain distance, so in the first graph you see over here that we can go pretty good up to 8 meters gap, but after that, we had significant drop in the accuracy of the prediction of the heartbeats. But because the loss keeps on increasing with the distance, you see those blue bars keeps on increasing. So we lose if we increase the distance. Then again, this is again the limitation of the antennas also we are using. If you use more powerful antennas, you can go a little further in terms of distance. The other thing also, as I mentioned earlier, that we looked at different postures. So if you are having the antenna reflecting from the front or from the back or from the left or from the right with different postures, then we compare the breathing rate and the heart rate measurements, and again it varies in there. So the front facing one will give you the best result. The answer is obvious. From the side, if you are taking left and right, the results will not be as good, because as we are capturing the movement of your chest. So the front facing one obviously will give the best result. So again, the last figure in here is the setup of the lab that we are measuring. So we used several studies for 20 different scenarios in 20 different rooms with multiple humans, single human, and in all these cases, we found that that after the accuracy of classification is improved through the learning, we get very good results in terms of measuring the heartbeat and the breathing rate. Okay, I have many other results in the paper, but I'm not going to get into too much of the details because of the interest of time. So again, this is in one of our labs. These are my students running the experiment. So they used, they have created different square blocks, and with the movement in each blocks, the stand in each block, how the measurement is impacting there. So in a way, again, as I said in the beginning, this is kind of, this is a proof of concept. It needs to be matured further to a point that you can have these type of antennas at home, where you'll use them for bandwidth, wireless bandwidth of 7 gigabits per second. In addition to that, they can be used for these type of application seamlessly and without you even doing anything. Okay, so for this part, the health part, we have come up with this model of measuring vitals. Right now, we are also looking at, can you measure blood pressure? Can you measure the what an oximeter does? So those are the things we are exploring now. So again, these are some of the things that I've already talked about. So let me move forward about another application which I have a lot of interest in also. And this is a very much applicable in the Indian context, which is where the economy is dominated by food and agriculture, and still technology has not found its way into the areas of agriculture and food as much as it should. So again, I'm not going to get into a broad or high level view, but I want to point out one aspect on how much capacity or how much more we can do with this new technology related to high frequency, this millimeter wave, in order to find applications in food and agriculture area. So I'll focus on food, and in this talk only on food, but before I end my talk, I'll generalize it, how this can be extended further. So again, there has been a lot of advances in Internet of Things, and you might be hearing more talks on Internet of Things. The question here is, can we monitor food quality? Now, there are some approaches which uses near infrared spectroscopy or laser imaging, etc., for measuring food quality. Those are all fine. But my goal here is, can we make it completely accessible by the consumers? So in order to make it consumer accessible, you need to rely on cheap devices, not specialized. So the existing approaches are all specialized, expensive devices, and they require invasive testing. So the goal here is, can I come up with an approach that I go to supermarket, grocery store, and I want to buy apples, and can I use my smartphone that I have in order to find out whether this is a good quality fruit or not? So that's the kind of thing. So this is the picture that I'm envisioning, that can you just pick out your phone and you want to buy some apples. Again, apple is just a very trivial example because it's simple to explain things. So can you just use that in order to find the quality? So that's the goal. So with low cost off-the-shelf devices, which are becoming very popular, can we do that? So the goal here is to investigate the feasibility of using, again, 60 gigahertz millimeter wave signals for estimating the sugar content in the fruits. Okay, I took sugar content as an example. You pick up any other chemical or any other thing, the approach will be the same. And there is a vested interest on why I picked up the sugar content, and I'll talk about that towards the end. So what is our ground truth? So the ground truth is, can we match the result by that you can object by that you get from a Brix meter. So Brix is a commonly used metric that measures soluble solid content, SSC. So the soluble solid content in an aqueous solution can be measured accurately by Brix. So 1 Brix referred to 1 gram of sucrose in 100 grams of aqueous solution. That's the kind of the standard measure. So we have Brix, we have bought those devices, and again, you can in the picture, I don't know why the colors didn't come. So the bar colors in my screen somehow is appearing all black. They are actually 3 colors, blue, green, and yellow, but they're more or less same. So it doesn't really matter over here. So for if you have, let's say, 12 grams, you have added either sucrose, fructose, and glucose, then that can be measured by the Brix shows the measurement correctly. So essentially that graph is showing that the Brix was calibrated to measure the fructose, sucrose, and glucose in soluble liquids. So here again, we have used the setup we have used is on the there is a Brix meter on the right that you see. Then we have an oscilloscope, and there are these 2 horn antennas pointing to each other. And We have software-defined radio that are programmable that we use in order to manage those two 60 gigahertz transmitter and receiver. So again, the schematic diagram is on the right, and where we basically have a baseband board where we send the signals, which basically is sent from one of the horn antennas of the transmitter. It goes through the fruit and it hits the receiver back, and the change in the signal quality is what we are capturing as the signature, and we derive a correlation of that. So if you look over here, the relationship between bricks, so bricks, just understand it as the ground truth of the measurement. So we are looking at sucrose, fructose, and glucose. So we could show that there is a correlation, there is a strong correlation between bricks and the RSS for 3 simple sugar solutions. What we did over here, I don't know whether you can see over here, between those 2 antennas, there is a bottle filled up with water. So we add certain level of measured sucrose, fructose, and glucose, and we try to measure, we try to draw the correlation of that. What we saw that the signal that is being captured at the other end has got basically, we find the RSS variation. It has a strong correlation with the content of sucrose, fructose, and glucose, and and we do all the calibration using the Brix meter in order to validate the correlation. So the goal here is, can we estimate now, if you don't have the Brix meter, can you just use millimeter wave reflection? Let's say if in future you will have millimeter wave capabilities in your smartphones, can we just use that in order to calculate the sugar contents in fruits? Okay, as I said, fruit is an example, could be any vegetable, could be any other agricultural product. Okay, but we are looking also on non-agricultural product also. So again, we saw that the correlation coefficients are close to 0.9, as you see. For the 3 we found 0.89, 0.96, and 0.86. So pretty strong correlation in there. So the bottom line here is the 60 gigahertz signal reflection is influenced by the amount of soluble sugar content. Okay, SSC, I call that as the SSC, and it is feasible to be used as a sensing modality for determining the SSC of the fruit. So given a solution with various SSC densities, we should be able to capture the Brix measurement from that. And this is where we have the soluble elements and we capture the Brix measurement. So this is how we do it. On the left picture, you see the picture of the apple over here. Now you have a transmitter and receiver. So when you send the 60 gigahertz signals, they go in all directions. Okay, all these blues are, they are scattered everywhere. Some of them are absorbed, the red ones are absorbed in here. Some of those are reflected back towards the receiver. So this is what we are capturing. And we even looked at different types of apples. Okay, if you take different types of apple, you form and you use again a machine learning algorithm for the classification. You find all these points which are based on the Bix calibration versus RRS, they cluster together in there, and that gives us an idea that we even can determine which type of fruit it is. Apple will give a different signature, oranges will give a different signature, and all. The other thing, again, there are many other effort. Again, this is also a published paper. You can check from my website, but there are many other issues that we also captured. Is the diameter of the fruit has an impact. How is the surface of the fruit? That has an impact. We looked at the flesh density and the structure of the flesh. So after doing all these studies, what we found that we have to really trim it down based on the fruit. There are impacts of fruit sizes and irregularities, but one thing that we found that if you take the flesh density, flesh inside the fruit, the flesh density of that will give you a good approximation of all the other aspects of the fruits. So again, purely using the RSS can yield lower Briggs estimation accuracy. Again, RSS is a very coarse grain statistics that is calculated for there. So we also use higher order statistics like mean, median, variance, standard deviation, skewness, kurtosis, and all in order to tune those, in order to improve the accuracy in there. Again, so we ran a lot of experiments, and again, I have all the results in the paper, which I won't be uh, showing all of them to you over here. So we took 100 different apples, different types of apples, 100 oranges, some of them are different types, and 100 kiwis, and ran a lot of experiments on there, on the diversity of shape, sizes, their surface roughness. As you know, the surfaces of kiwis are different than apple and oranges. The flesh structure, the flesh of oranges are completely the lower density than the apple flesh. So all this matters. We have done detailed studies of comparison of that. And on the left, you see, we also saw the impact of the measurement time and the position. So at what position of the fruit that you put your antennas in order to get the best calibration. Similarly, how long should you measure it? Again, all these details, after doing all these 300 experiments, we have figured out, what are the best practices in that. So as I said, the other thing is it's not only the RSS that we are looking at. We used, as I said, we have taken 300 fruit samples, and we used 4 different positions for 1.5 seconds for each of those positions. And we used different types of learning environment. Linear regression, random forest regression, and the support vector regressions. And again, the results for each of these I have shown over here on what we are getting. So there is a lot of work that we have done on different types of fruits and all. The goal here was to show that there is a correlation that can be captured. The goal here was not at all on identifying good apples versus bad apples or oranges and all, because we want to take this further out in order for bigger and broader agricultural applications. So the inferences from these studies that we found out is we wanted to show that it is feasible to use 60 gigahertz millimeter wave signal reflection to estimate the sugar content. And again, we showed how varying level of SSC affects the signal permittivity. And we used also, the test bed for all kinds of studies of different types of fruits. And we could show that the coefficient means the relationship between the actual Briggs measurement versus what we were getting was at an average of 85% accuracy. So which is not that bad for this application, but we are looking at broader applications. So one of the things that why I started looking at sugar, and there is a huge interest in that, as many of you may not know, UC Davis is almost the #1 in the world in winemaking. Okay, we take pride in being the pioneers in developing the science behind the wine industry. And again, in the entire university, the courses on winemaking are of the highest demand that far exceeds any other courses. So, and it is as you know, that it is a very high revenue market and all. So the goal here is the next step we are trying to see is, and wine is what? It's basically fermented sugar. So we want to see right now in the wine industry, the fermented sugar content, actually they measure the sugar content in a chemical analysis way. We want to see that can you measure the sugar content in the wine bottles, or even before the bottles, in the barrels and other containers in the winemaking industry, without even going through the chemical analysis? Can you have this completely touch-free type of making? So that's one application. The other thing is like in farming and all. So let me go to my last slides where I'll talk some about this. So we, again, as I said in the very beginning, my main point of this presentation was to get the message that millimeter wave, in addition to providing high bandwidth for communication and data transfer, it provides also a new opportunity for sensing. So one of the approaches that I said that you can have seamless, continual, you can have your heartbeat measured, 24/7, seamless, continual contact lens sensing. That will change the complete landscape of healthcare. So think about it, your heartbeat 24/7 is being monitored by your phone or by a device at your home. You don't have to wear your Apple Watches all the time to measure your pulse rate or anything. You walk into an office or walk into a room where this is fixed to the infrastructure, so all your vitals can be measured. Think about it that your blood pressure is being monitored at your whenever you are at home because of some devices connected to the wall, and you don't have to do anything in there. So again, this will be very useful in old age facilities, in nursing homes and others. They can leverage a lot of these type of applications. Similarly, in the food and agriculture side, I showed you about the fruit measurement and all. So there is a lot of interest in the food industry. Like let's say, I was talking to someone in Florida. Florida is kind of the orange capital of the world. There's a lot of citrus production over there. Now, when we are talking about, a type of, let's say, pest attack on one type of the farm, then it spreads far. It's very difficult to, keep track of those. But can we use some millimeter wave sensing in order to track the changes in those fruit, why some of them are getting spoiled on a real-time basis? The other thing is, can we fix, these type of antennas underneath a drone and fly a drone to measure, let's say, the water content of the soil, or some other density of the soil, or what is the condition of the plant in large farms and all. So drones provides another or open up another angle of opportunity for using or expanding the use of millimeter wave sensing. And again, these are two broad classes I have talked about. There are other applications that we are looking at. One of the biggest challenges in California are the wildfire. You must be seeing that in the news. So how do we, is there a role that millimeter wave can play in detecting the onset of wildfire, or predicting wildfires? So basically the broad area of climate change or the broad area of environment, can it be detected? The other thing is in terms of the air quality. I mean, think about the air quality issues in New Delhi. So, can we use some kind of sensing? While again, the key advantage over here is, I would say that this is at zero cost. When millimeter wave becomes very common, they will be there everywhere for data transfer, for communications and all. So for example, Wi-Fi and your cellular network is there everywhere now for communications and for data transfer. So this will be in addition to doing that. So that's why I said at almost no cost. These are some very useful applications we can derive and can make an impact as we move forward. So there might be many other applications that I may not have envisioned, but some of you can think about. So let me stop over here, and I will be glad to take questions.
May I ask?
Yes.
May I ask a question?
Yes, please. Please do.
Good morning, Dr. Mohapatra. That was a very, very interesting session. I have two queries. You talked of pulse rate and heartbeat being measured. Have you explored the possibility of using these in narco test? These are in non-invasive methods. So can it be used in narco test? Have you explored the possibility? It just occurred to me. And secondly, what is the effect of these waves on human body? Are they good for us?
Okay, so good question. So the first one, the answer is no, we haven't done, but that's a good thing, so the challenge in the narco test, we haven't worked on it, but we did think about it. And so we are trying to figure out a way. So prior to doing that, our next attempt is now on measuring BP. Okay. So we have made some progress, but here is the challenge. We are limited with the frequency band, 57 gigahertz to 64 gigahertz, and so we are talking about very high frequency. These frequency don't, in the normal sense, if you don't do anything else, they don't penetrate human skin. Okay, so going into penetrating the skin and measuring the blood, anything from the blood is difficult directly. However, as I said, if you think about it, most of the things we are kind of inferring our measurement from another signature. So we are trying to find out an intermediate signature and how to capture that. So that's our ongoing, once we get into this extracting measurement from blood, we can do a lot of testing related to, but that is extremely important, because as I said, can we do the oxygen content and what an oximeter does. So it will be very interesting if we can figure out the accuracy of the blood measurement. So like as I said, we are measuring the sugar content without touching the liquid at all inside a fruit. So can we measure the vitals from the blood without penetrating the skin, which at that high frequency we cannot do it. So we are working on that. The second question is high frequency. What again? I haven't done any study, but I haven't seen any study that has impact on human health because of the frequency. Just think about it. There are a lot of medical screening that are done through high frequency, but you could argue that okay, that are for a transient time. You go through the high frequency, get done with it. Here I am proposing to have it all the time. So if we, for example, if we are adapting 5G around 28 gigahertz or something, we are already getting into that high frequency. So I don't think there is enough long test environment that is done on the impact of human health. So it'll be hard to say, but so far I haven't seen any studies that show that there is anything, any negative impact on human health.
Thank you.
Thank you, sir. I have a question. This is Uday here. So Dr. Uday here from SRM University. A very nice talk, sir. So I have a question. There are two questions. One is with this horn antenna, how we can achieve multiple beams? That's first question. The second question is, it's related to this location of the object. And when you put this transmitter, you are sending some signal. You have to do some steering distance, everything. And the receiver also, you have to place the receiver in such a way that RSS should be maximum we have to capture. So how we are doing this?
It's a good question. Yeah. So it took a lot of time for us to program that to do it. So the challenge is if you are using horn antennas, so basically the receiver and the transmitter, because we are measuring the RSS variation, they have to beamed into the same object. So that's a very good question that I didn't talk about that. But the way we are doing that is so the basis that you saw, every time we put our antennas, as you might have seen in the picture, there was kind of a camera type of stand, which is sitting in this white circular thing. So this white circular things, they are platforms which are controlled through, so they're not like plain desk or table or anything like that. They are electronically controlled platform where we write programs to move them. So if this horn antenna moves, let's say by 2 degrees, they have even sub-degree accuracy. Then the other one, we move to certain degrees in order to make sure that they're pointing to the same object in there. So we have to do a lot of programming in order to do that, in order to get the correct measurement. So that's how we can reuse the angular space in there. A better solution in future would be to use an array of antennas where the cost will significantly increase, but the management of will drop down. But we wanted to come up with low cost approaches in order to do that.
Yes. So this thing we can use this machine learning algorithm for this finding out, right?
Yeah.
Whole understanding everything, reinforcement learning, and we can use kind of thing.
Yeah,
So
and
we
again, you don't have to go for any deep machine learning here. We could found that we could easily classify the RSS measurements pretty easily.
No. The thing is for this location thing to keep the location of this thing.
Yeah.
We need some learning algorithm. Then it will give a lot of advantage.
Right, and especially when you get into a new environment, you have to again, have the scheme learn the rooms, learn the size and the objects in the room and all that. Yeah.
Yes. And the other question is from the horn antenna, how we are getting multiple beams? Do we get multiple beams through the horn antenna?
So we are not actually using that aspect. We are kind of turning them in order to have kind of emulate multiple beams. But ideally, you can put multiple horn antennas. Horn antennas are expensive, so we ideally would use multiple of them, but we are trying to use the same two and turn them around in order to emulate multiple antennas.
Yes, other ways we can use this antenna arrays where digital beamforming we can do. So, but the problem is this cost will be huge. That is there.
Yeah.
Okay. Thank you, sir.
Thanks. Any other questions?
I see 2 questions here. Mr. Bipin Sartape, you may ask the question, your question, please. Please unmute. Okay, let me read out the question then. The question is that in a room, where many persons are available, what is the criteria for allocating multiple beams to each person? Can we determine the approximate age of the human based on the pattern of reflected beams and activities engaged? Was a person in joyful mood for a particular time, or whether a person is in a tense situation for a certain period? Can we find out that?
Yeah,
this is the question.
So the first part is if there are more people available, what is the, so we, again, so far based on, we are still working on this. If you have too many people packed in a room, then this will not work because it will be very difficult. But let's say there are 2 people, then you can easily detect. And we have been using the same set of antennas to do that. If you are talking about a meeting room and there are 50 people and all, this will not work. Okay, so that's why I said it's in home environment where you have 3 to 4 people, or in office rooms where you have 2 to 4 people or something. In there you can do, but beyond that, you will, even if you use a lot of antennas, you will not be able to solve the problem. The other question is interesting. Can we find out approximate age, the sentiments, and the answer is no. Think about it. It will. I mean, think about it. Even if you see a person, it's not that easy to determine the approximate age.
Maybe emotion detection. He may be meaning emotion detection, whether a jolly mood or angry mood, like that.
No, again, keep in mind that we are capturing the signals, the signature from the signals. Whether you are sad or angry, you will not make an impact on the RSS reflection. So
from the image only, feature detection, using feature detection, it will be possible, sir.
Exactly.
Exactly. The another question I see in the chat box, one question, and that
while we are using the millimeter wave for monitoring, okay. So what is the impact on human health? So I answered the question already, because we haven't seen any bad impact, but that doesn't mean that there isn't. But I think a longer study is needed in order to do that.
What is the radiation impact? Maybe he may be meaning
right.
that.
So it's not studied yet, but I mean, it has been studied, but no one has found any ill effect yet. Even, you see some things in the media that using cell phone continuously creates an impact on the brain, but there is no scientific proof yet. So this belongs to the same category. The next question is same thing related to the fruit.
Yes.
When you penetrate the fruit, does it have an impact? I don't think so. And again, so these are not radioactive radiation of any kind. These are very high frequency. You get exposed to high frequency even in your daily life, and you take a flight and all, you get exposed to a lot of this. So I think if there was any negative impact on high frequency on human body or on human food, we would have learned it by now. So I doubt whether there is an impact, but again, I won't make any definitive statement on that. Do you think it is feasible and effective to use millimeter wave to detect wildfires? We are working on that. We haven't. So the challenge in wildfire is there are just too many causes in there, and it's not like a one or two signature that for example, finding sugar content, there was a specific signature, we could capture that. Here the variance is too much, so we are still working on an approach where we are looking at we are going deeper into the physics part of it, the of high frequency, and see if we can make an impact. Again, I really don't have a clear answer on how to do that. That's something we are looking at. So at what angle we should, so we have seen, and I have, if you look at the paper that I have on my web, we have shown the results for different angles. So the smaller the angle, I mean, it's better to, if it is too small, we won't capture that. But if it is somewhere between 90 and 180, that's where we get the best result in terms of the fruits. For people also, we have found that that's the range we get better reading in the reflection in there. It also depends on the other material in the room. If there are like a big metallic wall structure, a big metallic almirah or something, then it distorts some of the signals.
Sir, continuing to this question, I had one more. That you said, na, if there are very much, means if there are multiple people here, then it would be very difficult, or we won't be able to do it. Would the reason for it be that some people will block the other people for the reading?
So the blocking part is one aspect, because you will try to measure the blockages through other antennas also if you have more antennas. But what the challenge happens is if these people move around, then in that case, you can easily detect a human being, but you cannot detect this human being is this person and that is that person. So if they change the space, this part, then it will be you will not get the accurate answer. But again, the other point that you brought up is a good point. The signals at this frequency will not penetrate through the human. So one human can overshadow. Forget about human. Even if you just open up a laptop, we notice that creates sometimes distortion to block a human measurement and all. So it is very sensitive. So one of the approaches that we have done in order to increase the robustness is we use, if you look at any room, the most clear path you have is the entire path under the ceiling. So underneath the ceiling, that entire about 1 feet or so, that whole area is completely free. So what we are trying to do is we are trying to create another hop, that you hop from any place into a ceiling structure and do all the reflection through there. So we are still working on that to capture this multiple human environment.
So in that continuation, it was something curious that I was thinking, that is it possible to from if we see it through the head, means because as we all know that all the signals come from brain only. So if we is it possible to take the rate from there, means the feeling something someone was when saying that if we can sense the tension.
No, we haven't. Okay, that's a completely different world. We haven't worked on capturing the electrical signals from the brain. I know that's what you're talking about. That we haven't looked at that area, and it is a completely different. It's a very complex world. We have to. I have seen some. We do some experiments at UC Davis where we get signals from monkey's brain and try to study on the impact of various activities and how they generate electrical signals in the brain. So we haven't, again, that's not related to this work, and that's a much deeper.
Yeah, actually, sir, when I was thinking now that there were multiple people, so people were blocking each other, so we cannot read the rates and everything. So I was thinking if it was possible to do it from the top side, from the head, because angle is wider, so we can take multiple people in account.
Yeah. No, that's what we are. When I said that we are going through the ceiling, that's what we are trying to do. We will bounce up the signals from the top because there is less restriction in terms of objects. If you look at any room, the 2-3 feet down from the ceiling, the space is completely interference free because there are no objects in there usually.
So, sir, you're agreeing that we can do that from the top?
Right, yeah.
Okay, thank you, sir.
Okay. I see almost all questions have been addressed by Professor Mohapatra. Thank you very much, Professor Mohapatra, giving a very interesting talk on millimeter wave sensing, which has a lot of potential for research. As you have already demonstrated a 60 gigahertz millimeter wave test bed at UC Davis, your experimental setup, and you have shown the evaluation and analysis you have taken varying the distance and postures of human objects. It's quite interesting for us to see and visualize that. Another the aspect that millimeter wave sensing can be used for this multiple beam. Using the multiple beam sensing, we can use accurate vital signal monitoring for multiple people. That is a great idea, and it will definitely going to help the society for monitoring or giving advanced medical care for aged community especially. And another point you demonstrated that how you can sense the sugar content in the fruit. That is very interesting topic, sensing through millimeter wave, and so we can develop locus devices which will be beneficial, highly beneficial to the society and the food industry. So today's lecture is quite interesting, what we find, and thank you, sir. Thank you very much for enlightening us on various aspects and applications of millimeter wave sensing. Thank you, sir. Thank you very much again.
Thank you, Dr. Das, and thanks to everyone. It was certainly my pleasure. Thank you, and have a wonderful day.
Thank you.